-6, 3, 5, and the plane x minus 2y minus 4z equals 8. Are people finished with this? Like, okay. Again, we're in section 12.5. This is number 72. And there is a good little picture that I will put up for a moment. Okay, when you're finding the distance between a point and a plane, what you're actually doing is you're projecting a vector from the plane to the point. So any vector will do, any vector that goes from the plane to the point will do. You project that onto the normal vector, and the reason why is the shortest distance from anything to something else is the perpendicular distance. So the normal is perpendicular to your plane, so if you project onto that normal vector, you're going to find the shortest distance. So that's what you are doing. So if you go back to your other, set of notes, and we remember about scalar projection.
What was the distance between a point and a plane?
Okay, so notice we're projecting onto n, and I'll just call the vector that the vector from the plane to the point, we'll just call it b. Okay, so I'm going to call that vector b because I think they're so I'm projecting onto n vector b, where b is a vector from the plane to the point, or vice versa. And
so b is that actual vector.
Yeah. It again, you could derive this initially, but you dot your two vectors, and then you divide by the vector the length of the vector you're projecting onto. Okay, again, where that comes from is really law of cosines. Okay, so like they have the angle, they have theta. It's really, really faint, but there's theta drawn up there. And cosine of theta is equal to adjacent over the hypotenuse. Okay, so the adjacent side is the length of your normal vector. Your hypotenuse is the length of b. But we just got done talking about how the angle between two vectors is equal to their dot product divided by their two lengths. And so if I were trying to solve for this, which is really what I'm trying to solve for, that's the component, then I want to multiply by the length of vector b. And again, I'm going over this because I know one day we were rushing through this in class, and okay, then this cancels out with that. So that's where the formula that I wrote up there, that's where it comes from. It comes from just using cosine and right triangle trig. So what I was calling the length of n means the component that I'm looking for. Okay, so we're going to follow that formula. It comes from definition of cosine. And so for our particular problem here, I need to find a vector from the plane to my point. So pick a point on the plane, just find a point you know is on the plane. So if x were 0 and y was 2, then this would be -4. To get +8, I would need this to be 12, right? So if z was -3, that should give me a point on the plane. 0 minus 4 plus 12 equals 8, check. So this is a point on the plane. So make a vector, so vector B is going to go from, actually the way they have it drawn from this point to the plane, the way they have it drawn, so I'm gonna follow that. Okay, so I'm going from this to here. Technically it would end up not mattering. So I'm going from the point out in space to my plane. So I went up 6, I went down 1, and then I went down 8. To go from the point out in space to the point on the plane. Okay, so this is from -635 to 0 to -3. Okay, that's my vector B in the picture. And then vector N we're given the normal vector of the plane. So B is 6, -1, -8. N is 1, -2, -4. And again, it's the normal vector of the plane. I can pick that out by just reading my plane. And then I want over the length of the normal. So the length of the normal will be the square root of 1 plus 4 plus 16. So 6 plus 2 plus 32. 6 times 1, -1 times -2, -8 times -4. And 21, is that right? 8 and 32 is 40. Okay, so this is the distance between the point -635 and my plane.